I'm going to explain the properties of an azeotrope for a binary solution that's in vapor-liquid equilibrium. But first, let's start off looking at ideal solution. This is just Raoult's law. We're plotting pressure versus mole fraction, and the bubble pressure is just a straight line. As we make the solution non-ideal, and let's do that by having activity coefficients that are greater than 1, then we get deviation. So now the bubble point line is not a straight line, but it's curved upward. If that gets to an extreme, this is how we can end up with azeotrope. So here's the equation. X1 is mole fraction liquid phase, gamma 1 is the activity coefficient for component 1, and P1 sat is the saturation pressure. So when the gammas are 1, we get this straight line, Raoult's law. Gammas are greater than 1, we get a positive deviation. And so let's look at the extreme when that positive deviation becomes large as the gammas become large. So the curves I'm going to show you are generated using Margulies equation, which relates the excess Gibbs free energy, gas constant, and absolute temperature to the mole fractions, and then two constants, A21 and A12, that are a function of how non-ideal. If these constants are positive, then we get the type of curve that we were just looking at right here. And we get the activity coefficients once we know the constants from these two equations. We can then use the modified Raoult's law. P is the total pressure, Y is the mole fraction of vapor phase, Y1 for component 1. And this allows, if we know X1, then we know Y1 from these equations. So here's an example of azeotrope. I'm plotting pressure versus mole fraction on the left, and then temperature versus mole fraction. So at 110 degrees, we get pressure versus mole fraction, and then I pick 1.6 bar to plot temperature versus mole fraction. You notice the deviation now is sufficiently positive that the pressure becomes higher than either of the saturation pressure. So this is P1 sat and this is P2 sat. And the azeotrope is this point. It's the point where the derivative of pressure respect to x1 is equal to 0. It's the point where x1 equals y1, and of course that means x2 equals y2. And it's the maximum in this plot, which means this now is a minimum. So if we have a pressure that's much higher than the saturation pressures, that means the two molecules prefer to not be near each other. In other words, the bonding between molecule 1 and molecule 2 is weaker than the average of the bonding between molecules 1 with 1 or 2 with 2. So molecules more likely be into the vapor phase, so the pressure is higher, or that means they boil at a lower temperature than either of the pure components because the weaker bonding between the unlike molecules. So this corresponds then to mixing in the liquid phase that would be endothermic, and these corresponds to the gammas being greater than 1. We get these positive deviations. Also means if we're modeling it by the Margulies equation, it means A12, A21 are positive, which means the excess Gibbs free energy is positive if we go back and look at the equations that relate excess Gibbs free energy to the constants A21 and A12. Well, the other extreme is when we have negative deviations. And let's look at what those curves would look like. So here are negative deviations, and they're sufficiently large that, again, we have an azeotrope. X1 equals Y1. The derivative of pressure back to X1 is 0. We have a minimum in pressure, which means we have a maximum in temperature. So the mixture doesn't want to be into the gas phase as readily as the pure components, which means it boils at a higher temperature. So the gammas, now gamma 1, gamma 2 are less than 1. GXS is less than 0. A12, A21 in the Margulies equation are negative. And this corresponds to exothermic mixing. So if we were boiling a vat of these two components, as we boil away material, the temperature increases, we'll eventually reach the azeotrope, and then we can no longer get separation by distillation because the liquid and the vapor have the same mole fraction. This is one of the significant issues about azeotropes.